Today we're going to continue talking about section 10.1, comparing to proportions. And today we're going to look at how to do a significance test to compare two proportions. So basically the idea is we want to see if an observed difference between two sample proportions is actually representative of an actual difference in the two parameters, or is it just due to chance variation. So we use a significance test to help us decide which of those two explanations makes more sense. So our null hypothesis is going to have the same general form of, our statistic or our parameter here equaling some hypothesized value. However, for the purposes of this course, AP Stats, we're pretty much just going to look at times when our hypothesized value is actually 0, which means that there's no difference between the two parameters. Those will be the cases we're going to solely look at, which means that P1 minus P2 is equal to 0 will basically always be our null hypothesis. Or if you, add P2 to each side of this equation, we can say that that means the same thing as a null hypothesis of P1 equals P2. The alternative, we can, use a greater than or less than or not equals alternative. And again, for each of those, you could move P2 over to the other side, and you could write them, this way as well. They mean the same thing. And then if the random normal independent conditions are met, we proceed with the appropriate calculations. So the test statistic that you calculate will be, standardizing the statistic of the difference in the two proportions you got from your sample. And the formula for a test statistic is statistic minus parameter divided by standard deviation of the statistic. So our statistic is p hat 1 minus p hat 2. Our parameter is 0 because, like we just said here, we're going to just do problems where the parameter is 0. So basically, the numerator here, that'll always be a 0. Then the denominator will be the standard deviation of your statistic. Now let's talk about that for a second. If the null hypothesis is true, that means P1 is equal to P2. Okay? But in reality, your p hat 1 and your p hat 2 might not be the same value, but our null hypothesis is that the parameters they're, trying to estimate is the same value. So what we do is we make up a new value that we call basically p, that is the pooled or combined sample proportion. Basically, you take it's kind of like an average of your p hat 1 value and your p hat 2 value. But it's basically a weighted average, because if one of these is a bigger sample than the other, we want it to count more. So basically you count up all your successes from both samples combined, and you count up both sample sizes combined, and you find this new proportion, which is going to be kind of halfway or part of the way in between your p hat 1 and your p hat 2. And that is the number that we use to find the standard deviation of your statistic. Right here is we use this, I guess, assumed value for p, which is kind of like an average of the two proportions you got in your two samples. And you plug this new proportion into our formula for the standard deviation of that statistic. And then this is the formula you get for your test statistic. Now, on the formula sheet, you can see here we've got for two proportions for this statistic. It'll obviously be centered at the, true difference of the parameters. The standard deviation is this formula. But then you'll notice here, we used this yesterday, is if we don't know the true parameters, we use our best guesses for which is p hat 1 and p hat 2. But then today, when we have a null hypothesis that P1 is equal to P2, we use this combined or pooled proportion. Now you notice in this formula here, basically they just factored out a greatest common factor here of, since the numerators are exactly the same, they just kind of factored out a GCF. this formula right here and this formula right here that I have are equivalent, and you can use whatever version makes the most sense to you. But then on the formula sheet, they also have a definition of this combined p-hat. The p-hat c here is number of successes from 1 plus number of successes from 2 over the sample size 1 plus sample size 2. So then putting that all together, we get this new inference method, which is called a two-sample z-test for the difference between proportions. And, you know, kind of comes together with all the stuff we know, random normal independent conditions. Your hypothesis is that the difference is 0. You find the pooled proportion of the successes in both. You then compute your test statistic, which is a z-statistic. You then find the area either to the right or the left, or a two-tailed test if it's a not equals alternative hypothesis. Let's take a look at an example. So researchers designed a survey to compare the proportions of children who come to school without eating breakfast in 2 low-income elementary schools. An SRS of 80 students from School 1 found 19 had not eaten breakfast. At School 2, an SRS of 150 students included 26 who had not had breakfast. And these are both large schools with more than 1,500 students at each. So do these data give convincing evidence of a difference in the population proportions? Carry out a significance test at alpha is 0.05 level to support your answer. So we're going to use the 4-step process, starting with the state, which is going to include our hypotheses. Now you could write the null hypothesis either one of these ways. P1 minus P2 equals 0, or P1 equals P2. And then the alternative, notice it's a not equals test because we just want to see if they're different or not. We don't have any preconceived notion about one being more than the other. We just want to know if they're different. And you could write the alternative either way. You then need to define what P1 and P2 are. So P1 is the true proportion of students at School 1 who did not eat breakfast. P2 is the true proportion of students at School 2 who did not eat breakfast, and then you also need to give your significance level of 0.05. Then we move on to the plan portion. So we name the inference method we're going to use, a two-sample z-test for P1 minus P2, the name of our inference method. We then check conditions. Random. Yes, we are told that there were 2 different SRSs performed, one at School 1, one at School 2. Normal. You have to check the number of successes and failures at each. So that's, sample size times proportion. So it's n times p and n times 1 minus p, and then n times p and n times 1 minus p. One's for population 1, one's for population 2. And we get all 4 of these numbers. We have to say all of them are at least 10. Then in the independence condition, again, just like we talked about yesterday, we've got 3 different sentences here. One where we state that the 2 groups are independent from each other. Basically, there's no overlap between these schools, so they are completely separate, which means they're independent. But then also individual responses within each school also need to be independent, so individual responses are independent. Then we also need to check the 10% condition for each school. So there are at least 800 students at School 1 and 1,500 students at School 2. Once conditions are met, we move on to the do portion. So we calculate that test statistic by first finding that pooled proportion. So basically, I add up all the successes at both schools and add up all the sample sizes from each sample, and I get this pooled proportion of about 19.57%. Notice that is, part of the way in between these 2 proportions that I got in my 2 samples. I then compute the test statistic by plugging in, my p-hat 1, plug in p-hat 2, plug in p-hat c, p-hat c, p-hat c, p-hat c, plug in n1 there and n2 there. You can type all that into your calculator all at once. You have to be careful with all your fractions and parentheses, but you should get 1.17 as your test statistic. Since this is a not equals test, it's a two-tailed test, so we want the area above that and below negative 1.17. We add them together, and you can use either table A or normal CDF, with the normal distribution centered at 0 and basically a standard deviation of the denominator here. You then need to, double one of the areas to get both tails, and you'll get a p-value of 0.24. And again, since that p-value is much larger than 0.05, we fail to reject the null hypothesis. There is not enough evidence to conclude that the proportion of students who eat at the two schools, the proportion of students at the two schools who didn't eat breakfast are different. We don't have enough evidence to conclude that. One thing to point out is that if you compare this test we just did to the interval we did the day before, they don't always give consistent results because when you do a confidence interval, you're using this formula, and when you're using a test statistic, you're using this formula for the standard deviation. But when you use a confidence interval, you use this formula, and these are not always going to give the same standard deviations, which means the results of a test and a confidence interval for the same data might disagree, especially if it's like really close. If it's close to 0.05, slightly above or slightly below the corresponding confidence interval might not completely agree. Then, of course, there is this significance test on our calculator. It's option 6, a 2-prop-z test, which you can find if you go to stat, test, and then you can see option 6 here is a 2-prop or 2-proportion z test. Then what you need to do is you need to type in the number of successes and the sample size for each group. So let's see, that would be 19 out of 80 for population 1, and that was 26 out of 150 for population 2. I'm doing a not equals test. I go to calculate, and you can see here that p-value of 0.24. There's the test statistic of about 1.17. And there's that pooled proportion right there for us. Let's take a look at another example here. High levels of cholesterol in the blood are associated with higher risk of heart attacks, so will using a drug to lower blood cholesterol reduce heart attacks? The Helsinki Heart Study recruited middle-aged men with high cholesterol, but had no history of other serious medical problems to investigate. So the volunteer subjects that'll come into play later, were assigned at random, so there is some randomness here, to one of two treatments. So you can see a bunch of men took a drug called gemfibrozil to reduce their cholesterol levels, and a control group took a placebo. During the next 5 years, 56 men in the gemfibrozil group and 84 men in the placebo group had heart attacks. So is the apparent benefit of gemfibrozil statistically significant? Let's perform a test. I will say that the significance level we're going to use here, because this is a drug study, we're going to use 0.01 for this one. Now, if you want to try doing this yourself first, you can hit pause here and then press play when you're ready to see the answer. So let's take a look at the answer. Again, 4-step process. Hypotheses, you could write it like the null hypothesis like that or that. Alternative was going to be a less than, because we do actually have an idea that this drug will help. So we want to make sure it actually helps. So we want a smaller proportion for the group that took the drug. You need to define P1 and P2 though. P1 is the actual heart attack rate for middle-aged men like the ones in this study who took gemfibrozil. P2 is the actual heart attack rate for middle-aged men like the ones in the study who take only a placebo. And like I said, we use 0.01 because we really want to reduce the type 1 error probability, because we really want to make sure the drug actually works. Let's see, conditions. You can look those over. And you maybe used your calculator to get these numbers, but that's the test statistic you should get. Your p-value is very small, which means that we have statistically significant results. We reject the null hypothesis. We conclude the alternative. Notice that I didn't check the 10% condition because we are not sampling without replacement. Also notice that my conclusion is just for those like the ones in this study.